That is where the Iranian nuclear program chose to hide. Not behind fences, not behind reinforced walls, not behind layers of surface-level security, behind a mountain. 90 meters of solid granite and compacted limestone, reinforced with blast-resistant concrete, poured in 17 consecutive stages, each stage denser and harder than the one before it. The Fordo fuel enrichment plant was never designed to look like a military installation. It was engineered to look like nothing at all. From the outside, the facility barely registered as a structure. A few surface access roads carved into the hillside near the city of Qom. A cluster of nondescript buildings that a passing satellite would categorize as agricultural infrastructure. Ventilation shafts disguised as irrigation outflows. Cooling pipelines buried beneath the same dry, chalky soil that had covered this plateau for centuries. And beneath all of it, carved into the bedrock of a mountain range that had stood for 40 million years, the most hardened nuclear enrichment complex on the face of the Earth. Every conventional military option had been studied and set aside. Penetrating bunker munitions dropped from high altitude could theoretically reach 60 meters underground in optimal geological conditions. Fordo sat at 90. Every ballistic trajectory, every cruise missile profile, every precision-guided munition in the Western arsenal had been modeled against the facility's depth. The geological surveys had been run and rerun. The blast propagation calculations had been reviewed by 3 independent teams of structural engineers with top-level clearances. The conclusion was always the same. There was no conventional kinetic solution. The mountain would absorb it. The centrifuges would keep spinning. The program would continue. But intelligence gathered over 22 months of careful, painstaking collection had revealed something the architects of Fordo had not fully accounted for. The facility needed to breathe. It needed to circulate coolant through the centrifuge halls to prevent the precision-balanced rotors from warping under the heat of continuous operation. It needed electrical power routed through external transformer nodes. It needed pressurized air cycling through ventilation corridors that, despite every effort to bury them, still made physical contact with the surface at 7 distinct technical access points distributed across the mountain's eastern face. Those 7 points were not doors. They were not entry hatches. They were not access corridors that a human being could navigate. They were narrow technical conduits, each barely wide enough for a maintenance technician's arm. But they were pathways. And they led, with the precision of an engineer's blueprint, directly into the mechanical nervous system of the facility below. The intelligence package included 3-dimensional modeling of each conduit's internal geometry, derived from acoustic analysis and thermal signature mapping conducted over 14 months. It identified the specific resonant frequencies of the centrifuge hall's geological substrate, the frequencies at which vibration would propagate most efficiently through the mountain's own rock. And it identified a device, compact enough to be carried by a single operator, that could be seated inside each technical conduit and left to wait. Not an explosive. Not anything that would trigger a seismic alarm. A resonance emitter. A device that would, at a precisely pre-programmed moment 72 hours after activation, generate a sustained vibration at a frequency specifically tuned to induce microfractures in the precision ceramic bearings of the centrifuge rotors. The damage would appear, to Iranian engineers, as spontaneous mechanical failure. No blast signature, no radiation release, no traceable origin point. Within 48 hours of activation, every centrifuge cascade in the facility would be rendered permanently inoperable. The mission had no official existence. No authorization chain that would survive a record's request. no operational order with a signature block attached. The officers who planned it had done so inside a compartment so narrow that fewer than 11 people in the United States government knew the full scope of what was about to happen. The submarine carrying the team had been on station for 11 days, holding depth in the deep water corridor south of the Strait of Hormuz, running silent on a course that would never appear in any official transit log. The crew knew their position. They knew their mission window. They did not know everything else. They did not need to. At 11:09 p.m., 47 meters below the surface of the Gulf of Oman, the submarine's navigation team confirmed the final approach geometry. The tidal current through the coastal inlet had been modeled against 4 months of archived oceanographic data. The IRGC Naval patrol schedule had been reconstructed from signals intelligence collected over 6 weeks. The satellite coverage gap was precisely 38 minutes wide, opening at 1:47 a.m. and closing again at 2:25 a.m. That window was the only window. Miss it, and the mission did not exist as a concept anymore. The dry deck shelter, mounted above the submarine's aft hull, had been pressurized and flooded 3 hours earlier. The SEAL delivery vehicle rested inside it, a low-profile, pressure-tolerant underwater transport designed to carry operators at depth without generating the thermal or acoustic signature of a conventional watercraft. It ran on an electric drive system that, at its lowest power setting, produced less noise than the ambient biological activity of the surrounding water column. The operators who climbed into it at 11:34 p.m. were already breathing through closed-circuit rebreathers that vented nothing to the surrounding water. No bubbles, no exhaust, no thermal plume. 12 operators in total, each carrying a load precisely calculated to the gram. The resonance devices, the conduit insertion tools, the thermal suppression equipment, the emergency extraction charges. Combined, the mission package weighed enough to matter. Each operator had trained for 16 months specifically for this profile. The team leader ran his final equipment check at 11:41 p.m. The sound of his own heartbeat was audible in the rebreather mask. The smell inside the dry deck shelter was cold iron and pressurized seawater, and the faint chemical tang of the rebreather scrubber canisters working at full capacity. The deck plates of the shelter vibrated almost imperceptibly with the submarine's idle reactor coolant system. It was the kind of vibration that, after 11 days at sea, a person stopped noticing consciously. But tonight, the team leader noticed it. He noticed every detail with the hyper-sharpened clarity of a man who understood that the environment was about to get significantly less forgiving. At 11:58 p.m., the SDV cleared the dry deck shelter and descended to its transit depth. The submarine fell away behind it and above it, retreating to a holding position 8 nautical miles offshore. The SDV's navigator tracked their progress on an inertial navigation display that received no external signal of any kind. No GPS ping, no radio query, no electronic emission that could be detected, identified, or traced. The display updated purely from the vehicle's own motion sensors, calculating position from acceleration, rotation, and time. It was accurate to within 4 meters at the distances they would travel. 4 meters was the margin between the planned route and the granite walls of the underwater approach channel. The coastal inlet was narrow. Narrower, in places, than the mission planning imagery had suggested. The bottom rose sharply as the SDV transited through the outer channel, forcing the navigator to trim buoyancy manually 3 times to avoid contact with the seafloor. The water temperature dropped noticeably at the channel's midpoint, where a cold, fresh water seep mixed with the Gulf's saline layer and created a density gradient that tried to push the SDV off its planned heading. The pilot corrected. The navigator updated the trim. The vehicle held its course, and then, at 12:44 a.m., the navigator saw it. He saw it as an acoustic anomaly on the SDV's passive sonar display. Two faint but structured signals spaced approximately 40 meters apart across the channel floor. Not geological, not biological. The spacing was too regular. The frequency signature was too consistent. These were transducer arrays, passive acoustic monitoring buoys, moored to the channel bed at intervals that, when cross-referenced with the known geometry of the inlet, created an overlapping detection grid. They were not in the pre-mission intelligence package. They had not been there during the last confirmed survey of the channel, conducted 14 weeks earlier. Someone had installed them recently, quietly, without broadcasting their presence, which meant Iran's underwater security posture for the Fordo access corridor had been upgraded, and no one outside of Tehran knew it. The SDV had 63 seconds of current-driven drift before it would enter the detection envelope of the nearest buoy. The team leader processed this in approximately 3 seconds. The abort protocol was a single phrase, pre-agreed, that would initiate an immediate reversal of course and a full-speed return to the submarine's holding position. The abort protocol was the safe option. It was also the option that meant the mission did not happen, that the centrifuges kept spinning, that the enrichment program continued, that 72 hours from now, Iranian engineers would bring their new Cascade array online and compress the program's timeline to a threshold that intelligence analysts had described, in writing, as strategically irreversible. He did not transmit the abort phrase. Instead, he keyed a single pre-agreed signal to the pilot, 2 short pressure clicks on the vehicle's internal communication line. The pilot understood immediately. He reached for the SDV's thruster control panel and powered the electric drive down to 0. In the same motion, he switched to manual ballast control and began the most precise buoyancy adjustment of his career. The SDV became, at that moment, not a vehicle. It became an object, a neutrally buoyant, inert object drifting on the natural tidal current of the channel, generating no acoustic signature beyond the passive noise of water moving around its hull. The team held their breath in a metaphorical sense. The rebreathers kept working, but no one moved. No one shifted weight. 12 operators became statues inside a steel cylinder drifting blind through a 40-meter gap between 2 acoustic sensors that were, at that moment, actively listening. The drift took 4 minutes and 19 seconds. It was the longest 4 minutes and 19 seconds in the collective operational memory of everyone aboard. The starboard buoy passed 8 meters to the right of the SDV's hull. 8 meters. The detection threshold of the array, based on the acoustic signature of the SDV at its lowest power setting, was estimated at 6 meters. The margin was 2 meters. In a channel 60 meters across with a 4-meter depth envelope and a tidal current that fluctuated by 15% over a 40-second cycle, 2 meters was not a margin. 2 meters was a prayer. The SDV cleared the grid at 12:53 a.m. The pilot restarted the drive at minimum power. Nobody acknowledged it. There was nothing to say. They reached the insertion point at 1:31 a.m. The beach was a narrow strip of gravel and compacted salt flat between the water's edge and the base of the hillside access road. It was invisible from the nearest IRGC checkpoint, screened by a rocky outcropping that the mission planners had identified as the only geometric blind spot in the facility's surface security camera coverage. The operators beached the SDV in water depth sufficient to keep the vehicle fully submerged, anchored it to a pre-surveyed rock formation, and moved onto the gravel in single file, weapons secured, equipment checks running in silence. The hillside was 340 meters from the water. The 7 technical access points were distributed across a 180-meter horizontal arc on the mountain's eastern face, at elevations ranging from 12 to 31 meters above the road surface. Each point required a single operator to approach, confirm the conduit geometry against the pre-mission imagery, seat the resonance device at the correct insertion depth, verify the activation timer, and withdraw. The total planned time on target was 11 minutes. They had been allocated 14 before the satellite window began to close. At 1:44 a.m., with the team moving up the slope in a staggered formation, the point man raised his fist. The column froze. Above them, the sound of a quadcopter rotor became audible in the dry night air. An IRGC reconnaissance drone, small enough to carry in a backpack, was conducting an unscheduled sweep of the facility's eastern perimeter. It was not in the patrol schedule. It was not in the threat matrix. Somewhere, at some point in the past 14 weeks, the IRGC had added an ad hoc drone patrol to its security rotation, and that addition had never been collected. The drone was running a thermal imaging sensor. Every warm object on the hillside was visible to it. The team deployed thermal suppression blankets in 4.2 seconds. The blankets were designed to reduce a human being's surface thermal signature to near ambient temperature within 6 seconds of deployment. Near ambient, not zero. There was a window measured in seconds, during which a careful operator reviewing the drone's thermal feed might notice 12 shapes on a hillside that had not been there before. The drone approached from the north, tracking a systematic grid pattern, its camera sweeping in 4-second arcs. It reached the team's position at 1:46 a.m. and began its turn. The intelligence officer, flat against the hillside with his blanket deployed, had exactly one option. He had been carrying a thermal decoy unit in his left cargo pocket since the SDV departure. A compact device that, when activated, produced a heat signature and minor motion signature consistent with a mid-sized mammal, calibrated to the local fauna profile of the Calm Plateau. He extended his arm as far as the blanket would allow, pointed the device at a depression in the ground approximately 90 meters upslope, and triggered it. The decoy activated. Its heat bloom appeared on the drone operator's screen as a 4-legged shape moving across the rocky ground in an erratic, organic pattern. The drone turned to follow it. For 11 seconds, it worked. The drone operator tracked the decoy upslope, and then, in a decision that reflected either exceptional professionalism or simple instinct, the operator dropped a micro-illumination flare. It was the kind of flare used to confirm visual identification of a heat source in uncertain conditions. A small device, bright enough to illuminate a 40-meter radius on the ground. It was already falling when the intelligence officer registered the launch. The flare would reach the ground in approximately 4 seconds. At the point of impact, it would be close enough to the team's position to render the thermal blankets meaningless. Close enough to make the shapes on the hillside visible to any camera with a basic optical sensor. The point man did not wait for an order. He'd been watching the flare's trajectory since launch. He pulled a pre-charged compact air canister from his chest rig and fired a tethered hook device upslope at a shallow angle, latching it to a rock formation 8 meters above and 12 meters lateral of the team's position. The tether was preloaded with a reflective surface. In the 2 seconds before the flare reached peak illumination, The reflective tether was taut across the hillside, positioned between the drone's camera and the team. The flare lit up the rock face. The camera saw the tether's reflective surface. It saw the false edge of a geological feature. It did not see 12 operators pressed against the mountain. The drone circled once more and resumed its scheduled grid pattern. Nobody moved for 90 seconds. At 1:49 a.m., the satellite window was open. The mission clock was running. 14 minutes on target had contracted to 9. The team leader made the assessment without hesitation. 3 of the 7 access points were designated priority targets. If only 3 devices could be placed, those 3 would be placed. They were positioned at the conduits feeding the primary ventilation corridor and the main coolant distribution manifold, the 2 systems whose compromise would propagate the most efficiently through the facility's mechanical infrastructure. 3 devices, instead of 7, would achieve perhaps 60% of the projected program disruption. 60% of an irreversible outcome was still irreversible. The insertion teams moved to their designated points at 1:50 a.m. The technical specialist on each pair worked in near absolute silence, using insertion tools designed to minimize acoustic contact with the conduit walls. Each resonance device seated with a soft, definitive click. The activation timer was set via a magnetic interface that required no electronic emission and generated no detectable signal. The device confirmed its ready state through a single micro-vibration feedback to the operator's fingertip. 90 seconds per point. 3 teams. 4 minutes and 30 seconds total. Each operator withdrew, stowed tools, and moved to the pre-designated collection point on the slope. At 1:54 a.m., 6 operators were moving back down the hillside toward the beach. The 7th had not yet signaled completion. The demolition specialist, working on the lowest access point, had encountered a conduit sealed with a secondary closure plate that was not present in the mission imagery. The plate was a simple mechanical device, a threaded ring collar, but removing it silently and in the dark with gloved hands at a pace that didn't trigger acoustic contact with the metal housing was a problem that required time. He had 40 seconds before the team's extraction timeline became unrecoverable. He made the decision that every operator in his position would have to make in that moment. He stripped off his outer glove, exposing his right hand to the cold metal of the collar, and worked it by feel alone. Metal on metal. His fingers read the thread pitch, found the engagement point, and turned with steady, calibrated pressure. The collar released at 37 seconds. The device was seated. He was moving at 39 seconds. The beach at 2:03 a.m. The SDV was exactly where they had left it. The operators entered the water in pairs, moving to the vehicle without visible surface disturbance. The last operator pulled the anchor release, and the SDV drifted clear of the rock formation, fully submerged, before the pilot engaged the drive. They were moving at 2:06 a.m. They had 19 minutes before the satellite window closed. They needed 12 minutes to clear the acoustic buoy grid. At 2:09 a.m., the submarine's electronic warfare officer, monitoring from his station at depth 8 nautical miles offshore, registered the acoustic signature of an IRGC coastal patrol vessel turning on an intercept heading in the outer channel approach. Its hull-mounted sonar was active, pinging at a medium-range search frequency, painting the channel in overlapping arcs of sound. Someone at the IRGC facility's command post had noticed something. The drone report. An anomaly on a coastal camera. A gut feeling communicated over a radio network that the electronic warfare officer was monitoring in real time. The patrol vessel was moving. If it reached the outer channel entrance before the SDV cleared the buoy grid, the pinion would cover the gap, and the SDV would be inside its detection cone. The electronic warfare officer had been authorized to use the acoustic countermeasures array under one specific condition. That condition existed at 2:09 a.m. He activated the submarine's bioacoustic projection system, a system designed to replicate the acoustic profile of large cetacean migration. The sound of blue whales, a biological pattern that any experienced sonar operator would recognize immediately as a natural event, propagated from the submarine's hull northward through the water column. It was loud enough, in the specific frequency range that made it seem genuinely organic, to attract the attention of any sonar operator listening on that heading. The IRGC patrol vessel turned north. It took them 4 more minutes to resolve the buoy grid passage. The pilot ran the same zero-drive drift technique through the gap, this time with the additional pressure of knowing the patrol vessel was in the outer channel and might return at any moment. The drift took 3 minutes and 58 seconds. The SDV cleared the grid at 2:17 a.m. The drive engaged. The vehicle ran at full power for the open water approach leg. The submarine was exactly where its navigation track said it would be. The dry deck shelter received the SDV at 2:44 a.m. The shelter drained. Pressure equalized. The hatch opened. 12 operators, no injuries. The submarine came to its transit depth and turned southwest at 2:51 a.m. It did not increase to maximum speed. It did not need to. Speed produces noise, and this submarine was not in the business of producing anything that could be heard, tracked, or recorded. It moved at the pace of a vessel that had no reason to hurry, a vessel that officially had not been there. At 4:18 a.m., still moving south-southwest through the deep water corridor, the submarine's sonar team registered a faint, localized seismic event propagating through the lithographic layer beneath the calm plateau. Not an earthquake. Too shallow, too localized. The team leader was in the crew mess, drinking coffee that was too hot and tasted like tin, and someone passed him the note with the seismic data. He read it once. He did not react visibly. He folded the note, put it in his shirt pocket, and finished his coffee. Whatever had happened in the mountain behind them, it had not been the 3 resonance devices. Those were set to activate 72 hours from now, during the Iranian facility's scheduled maintenance cycle, when the anomaly would be most difficult to distinguish from mechanical failure. What had just registered on the seismic sensors was something else. Perhaps a geological coincidence. Perhaps something structural inside the facility whose stress had been accumulating for longer than anyone knew. The team leader did not speculate. He was not in the speculation business. The submarine crossed the operational boundary at 6:33 a.m. and reverted to its logged transit profile. From that moment forward, its navigation record showed a routine patrol. Its crew manifest showed a routine watch rotation. Its communications log showed nothing that would attract the attention of anyone reviewing it in any context, at any classification level, at any point in the future. The operation had lasted approximately 7 hours from SDV launch to area boundary crossing. Of those 7 hours, 11 minutes and 42 seconds had been spent on target. 3 resonance devices had been seated in their designated conduits. 0 physical traces had been left behind. 73 hours later, at 3:30 a.m., Iranian technicians at the Fordo fuel enrichment plant initiated their scheduled maintenance diagnostic on the primary centrifuge cascade array. The diagnostic registered anomalous bearing vibration across 18 centrifuge units in the priority cascade corridor. By 5 a.m., the anomaly had propagated to 44 units. By 9 a.m., the engineering team's assessment was complete. The centrifuge hall would require full mechanical inspection and bearing replacement across the primary and secondary cascade arrays. The process, at the facility's available maintenance capacity, would require an estimated 14 to 18 months. The new cascade activation, the activation that had been 72 hours from completion at the moment the SDV left the channel, was suspended indefinitely. No explanation for the bearing failures was found. The investigation concluded mechanical fatigue consistent with extended high-speed operation. A geological survey found no anomalous seismic activity beyond a minor tremor on the night of the failure, assessed as natural. No external cause was identified. No security breach was reported. No adversarial action was suspected. The mountain stood. The facility sat silent inside it. The program's timeline, measured in days, was now measured in seasons. Somewhere in that gap, a decision had been made, acted upon, and completed by people whose names would not appear on any document associated with the outcome. The centrifuges stopped. The operators were already home. The submarine's reactor ran quietly in deep water, its crew standing their watches, recording nothing unusual in the log, 90 meters deep. 12 elite operators. 11 minutes and 42 seconds on target. 3 resonance devices placed. 0 traces recovered. 0 breaches detected. 18 months of adversarial nuclear timeline removed from the equation. The mountain was built to be impenetrable. And it was. But the men who entered never touched the mountain. They touched the systems that kept it alive. In the silence between the spinning and the stillness, they proved what no hardened bunker has ever successfully refuted. The deep does not protect what hides inside it. It only makes the hunters quieter.